Now, that's adding vectors. There are different ways to multiply vectors. One, we can take a vector and multiply it by a scalar. All the scalar does is lengthen or shorten the vector, or if it's negative, the scalar is a negative number, it'll flip the direction by 180 degrees. So if this is vector A and I multiply it by the scalar 2, all I do is take vector A and double its length. If I multiply it by minus 1/2, I both shorten it and notice I flip the direction around. And that is just taking a vector and multiplying it by a scalar. Now, I can also multiply vectors together. And there's two ways to do that. I can multiply the vectors so that I get a scalar, or I could multiply the vectors so that I get another vector. The first one is called the dot or the scalar product, and it is simply defined as a dot product. That's what this dot right here means. And you simply take the two x components, multiply them together, and then add the product of the two y components. That is more or less the definition of a dot product. We can also calculate it, and we're not going to derive this since this is not a math class, that it also can be found by the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle in between the two vectors. And remember, this is not the angle for either individual vector, it's the angle in between the two vectors. Now, one way to interpret what this dot product actually means is, notice if I take A and I multiply it by b cosine theta would be this side of a right triangle. Namely, there's my right triangle, and it's this side right here. In a sense, it's how much of b is in the same direction as A. And that's this component right here of b. It's not technically the x component. In this case, I happen to have drawn A in the x direction. Instead, it's how much of b is in the same direction as A, regardless of what direction A is pointed in. Now, we can take some special cases, namely, what happens if this angle happens to be 90 degrees? I have two vectors that are perpendicular to each other. Note that that's the cosine of 90 degrees, that is 0. So the dot product of two perpendicular vectors is 0. If the two vectors are parallel, then the component of b that's in the same direction as A is all of b, then the dot product is as large as it can be. Then it's just the product of the two magnitudes. Notice if this vector is pointed at greater than 90 degrees, or kind of in the opposite direction as A, then the cosine of the angle in between them will be negative, and the dot product will be negative. So dot products, although they are scalars, can be positive, negative, or 0. And it kind of is a measure of how much of these two vectors pointed in the same direction. Are they perpendicular to each other, or are they in opposite directions? So if the dot product is large, they're in the same direction. Dot product is small, close to 0, they're close to being at right angles. The dot product is negative, then they're pointing in opposite directions. Another thing we can do is we can use the dot product to find the angle between two vectors. So that if I have the components of both vectors, I can calculate the dot product by just multiplying the components and adding them. Then I can find the magnitudes of each vector using Pythagoras. Then I can use this part of the equation right here to find the cosine of the angle in between them. It's the dot product divided by the product of the two magnitudes. That will then give me the angle in between them. Now, one question I'm going to ask you, and I want you to answer it in a little box on the side, namely, what is the component of a dot product? So take a moment and answer that. I hope you realized that was actually a stupid question. It's a scalar. Scalars don't have components. In no sense is this product right here a component, because I'm adding it to that number. When I do this addition, all I get is one number, and I'm not distinguishing between this product and that product. It's a scalar. There is no components. It has no sense of direction. Therefore, the answer to the question is that makes no sense. Now, take a few minutes and basically compute these dot products as well as this one. Here I've simply displayed the vectors graphically, and here I've given you their components, and enter the answers in the little box on the side. So here are the answers. You take the two x components, multiply them together, add them to the two y components, and notice you get a single number. 42 doesn't care how much of it came from this product and how much of it came from that product. The dot product is merely the number 42, and that number 42 has no sense of direction. Here we do the exact same thing. We come up with -4. Here, since we don't have the components, we would do this by multiplying the magnitudes of the two vectors together times the cosine of the angle. The angle is greater than 90 degrees, and therefore the dot product ends up being negative. Now, the other way to multiply vectors together is to produce another vector, and this, of course, is called the cross product. And this is the way it's represented. It's the vector A, then this symbol, this cross, times the vector B. Now, I'll write down this equation right here. Do not worry about it. We will never be using it. This is the formal definition of a cross product. And that's if you really want to compute the cross product using the components. We will not be using that. Instead, we'll calculate the magnitude of the cross product using this analogous formula to the dot product, except rather than the product of the magnitudes times the cosine, it's the product of the magnitude times the sine of the angle in between them. This can be derived from this formula. We will not do that. We will simply take that the magnitude of the cross product is A times B times the sine of the angle in between them. Again, remember, this is the angle in between vectors A and B. One way to interpret this is this product right here ends up being the area of this parallelogram formed by vectors A and B. The direction given by this formula right here can also be found by using what is known as the right-hand rule. The right-hand rule is you take your index finger, put that in the direction of the first vector, take your middle finger, put that in the direction of the second vector, then your thumb will point in the direction of the cross product. And you have to use your right hand, and that's simply the way we have defined the cross product. It follows this so-called right-hand rule. And we do that because this is how we define our coordinate systems. This is the x-axis, this is the y-axis, and this is the z-axis. Axes that form along the directions of these three fingers of your right hand are called a right-handed coordinate system, and that is the way we define the x, y, and z axes. And therefore, that is the way we define cross products. The z-axis is defined to be the cross product between the x and the y. And that relationship defines the Cartesian coordinates in 3 dimensions. Note one thing that's a little bit different about the cross product. It is inherently 3-dimensional. If A and B are in one plane, the cross product, A cross B, is not in the same plane. It's perpendicular to those two planes, because your thumb would always be perpendicular to a plane containing your two fingers. That's why the convenience of using the right hand. Again, just like with the dot product, there are some special angles, like what happens if the two vectors happen to be parallel to each other? Well, if they're parallel to each other, theta is 0 and the cross product is 0. So the cross product between two vectors pointing in the same direction, like for an example, the cross product of A and itself would be 0. The dot product of A and itself would be a large number because A and itself would be pointing in the same direction and the cosine would be 1. On the other hand, when we have a cross product, the cross product goes to 0. If the two are perpendicular, then this parallelogram becomes a rectangle and the cross product becomes as large as it can be. Now, take a stab at calculating these cross products, noting you're going to be using the right-hand rule to determine the direction of the cross products. So what I want you to do is enter the magnitude and direction of both of these cross products. Direction will be up, down, left, right, pointed into the screen or pointing out of the screen. So take a stab at doing that. Okay, the magnitude of the cross product will just be A times B times the sine of the angle in between them. That's 6.93, and it's the same for both of them. It doesn't matter what order we do the cross product. Now, if you take and put your index finger in the direction of A, and your middle finger in the direction of B, your thumb will end up pointing out of the screen. And it has to be pointing in a direction that's either into or out of the screen, because the screen will be defined by a plane containing the two vectors, because they're both on the screen. The cross product, therefore, will be pointing either into or out of the screen. A cross B turns out to be out of the screen. B cross A, on the other hand, you have to flip your fingers around, and now your thumb points into the screen in the opposite direction, which then tells us that the cross product is not commutative. It is what is known as anti-commutative, because A cross B equals minus B cross A. They have the same magnitude, but they have opposite directions. We call that anti-commutative. Now, an interesting question would be, we talked about vector addition and subtraction and multiplication, but we never talk about vector division. I want you to think about that for a minute and wonder, what exactly is division, and why don't we ever divide vectors? Now, of course, we can, in a sense, divide vectors by multiplying them by fractions, but that's not what I mean. What I want to know is, can we take one vector and divide it by another vector? Vector A divided by vector B. We don't talk about that. Why not? Now, notice what I'm going to do is put a link on the side here, so if you want to actually find what I thought was a pretty reasonable answer to the question, you can follow that.